Once more, we see if we move along a constant pressure line, which hasn't been drawn very well. The pressure here looks a lot higher than it does here. We go from a solid state as volume increases and temperature increases. We reach a state of the matter where we have a solid-liquid combination. Then we'll go through a little phase here where it's just liquid before it crosses over into the liquid-vapor region. And then again into the gas-vapor region. If we look at this curve where we have a constant temperature, what's happening is we move along this curve. We're compressing the substance. So we move along here, we're in the gas-vapor region. We compress it enough, now it's a solid vapor. Now if we continue compressing it, we can get down into the state here where we just have a solid. Okay, the volume is low enough at this temperature, it goes into a solid state, and remains in that solid state. Okay, if we go to slightly higher temperature and do the same kind of a compression, we have a curve that goes along here, up here, and so forth. Now what's happening? That means we go from a gas state to a liquid vapor state as the volume decreases. In other words, as we compress the substance. Okay, let's see, we're here. And then we go to a liquid state with further compression, then a solid liquid state, and finally a solid state. Now there are two projections of this graph. Okay, if we project the graph in this direction, or project the solid in this direction, and if we look at these blue lines here, what do we see? Well, these blue lines project onto this surface, which is a pressure versus temperature surface. I don't guess I have the pressure in there. I think we can see enough this way. Okay, we have pressure versus temperature. This is just the graph that we just saw. The sublimation curve, the fusion curve, and the vaporization curve, and the triple point. Okay, the triple point corresponds to this point here, where we have gas, vapor, liquid. I'm sorry, this is not the triple point. Triple point is down here, and this is your critical point. The critical point where you have gas and liquid coexisting corresponds to a point on this three-dimensional diagram. Remember, this three-dimensional diagram here takes volume into account along with pressure and temperature. For a given volume, this actually, this point only exists for this volume. Never mind what I was going to say. It's not relevant. Okay. Again, we see that this part of the curve here projects to here. This part of the curve, which is pretty much a straight line, goes here, and that's your transition between solid and liquid. And the transition between liquid and vapor indents a little further, a little deeper into this than this thing does, and gives you this part of the curve, which goes up to your critical point. Your triple point is the point where your solid, your vapor, and your liquid all exist together, which is in here. If you have a point along this line here, you're at a border between solid, vapor, and liquid. And this point right here, you have solid, vapor, and liquid all converging. That's your triple point. It exists only at certain volumes for a given substance. Now this would be a diagram for a given substance, for example, water. So you can think of water. Now we can project back to this diagram, the green projection. This is pressure versus volume. And what happens to pressure versus volume? As volume increases, at low pressures, for a certain temperature region, you can have the solid vapor region, which hasn't been labeled here. Okay, at slightly higher pressures, you have the liquid vapor region. And you have the various separations. This line here corresponding to this line corresponding to this, and this line corresponding to this line. This line indicating where the solid state begins. Between these two lines you have the solid liquid state. Up here you have the liquid. So that we can see this entire behavior of a given substance from this three-dimensional diagram, and sometimes by considering its two projections.